Hello, my name is Alex. You're watching the first video in a series where I want to show how to run AI agents securely. In today's episode, I will focus more on the security concepts and how to apply them to coding assistants, such as Visual Studio Code and Cloud Code. In later videos, I will show how to set up more advanced security controls and how to run autonomous agents securely. This video will be roughly an hour long with a few demo sessions. It will be packed with different information, so feel free to pause the video and ask your questions in the comments below. So the plan is to first explain what supply chain attacks are. Then I will show what is the prompt injection attack and how it may happen when working with coding assistants. We will look at the industry best practices, in particular the sandboxing and the zero trust cybersecurity framework. I will then discuss why the sandboxing and zero trust standards are quite hard to apply on a company scale. Then I will show my implementation of the zero trust architecture for AI agents, and I will wrap up with a few words about how your company can use my zero trust runtime to minimize risks and leverage the power of AI agents. So let's start with the very familiar Visual Studio Code. This video about cybersecurity for AI agents need to first explain what are the risks we are trying to mitigate. Today we'll focus on the risks for the most widespread kind of AI agents, the so-called human-in-the-loop coding assistant. Nowadays, all popular IDEs, so integrated development environments, have extensions for AI assistants. For example, in this case, it's a GitHub Copilot, but it could be Cloud Code or Codex. They publish their own extensions for both Visual Studio Code and for JetBrains IDEs. And of course, those coding agents or coding assistants, they also exist as a standalone, pure terminal interface, so they don't really need an IDE to work. But the attack vectors which I show today, they're relevant for both the IDE-based coding agents and for terminal-based. I'm talking specifically about prompt injection and supply chain attacks. These attack vectors existed long before AI agents gained widespread adoption. Previously, we called them social engineering attacks, and we tried to educate the people in IT to not fall the victim of such social engineering attacks, and the poisoning of popular open source libraries was happening long before the AI era. But the advent of large language models increased those risks considerably. Many industry experts say that AI is the universal multiplier. The AI agents gave us the real productivity boost on one side, but the classic social engineering and supply chain risks have also been greatly amplified. Let's look at the tools inside my coding agent to understand why. So here my GitHub Copilot extension can execute shell commands. It can edit files, and it can connect to servers on the internet, download web pages, and search the web. So if you see on the complete list of the default agent, it's already quite big, and I would say unnecessary or unnecessarily dangerous. Because the agent can execute any commands it deems useful, this means that the agent can inadvertently use all my SSH keys on this computer, all cloud credentials, all Git credentials, and file servers, and even look through my shell history. Crucially, this also means that the agent have indirect access to the browser sessions. And those session cookies, they are essentially my credentials to all other company resources, which are normally behind the two-factor authentication. But because I access email and chat on a daily basis, my browser has those cookies saved on disk, and theoretically an agent can exfiltrate those cookies and have such a backdoor access to all the other resources which are authenticated inside an active browser session. And of course, my computer has direct internet access, so nothing stops the misbehaving agent from stealing my data and sending it to an attacker, or maybe encrypting the entire hard drive for a ransom. First, I wanted to show you the supply chain attacks. The classic example for Visual Studio Code is the supply chain attack through the extensions. Here I'm searching Mermaid, but first let's look at the list of recommended extensions, like 8 extensions. It is obviously not enough. So normally when I develop in some programming language, I will install a programming language for Go or for Python. If I want to create mermaid diagrams, I will install some extension for a mermaid diagram. There is luckily a signed extension and another one which is already deleted, but there are also hundreds of extensions which were never validated, and they seem to be helpful for writing markdown mermaid diagrams and maybe markdown files, but I don't really know if those were actually validated to be secure. Indeed, this became an attack vector. So if we look at the scientific studies, these researchers found in 2024 that 5.6% of inspected extensions showed suspicious behavior. And another paper, also in 2024, inspected more than 2,000 extensions and found that 8.5% were exposed to credential-related data leakage. And those were the good old times, because now AI has made it extremely simple to develop and publish malicious code. So the number of cybersecurity incidents is growing fast. Attackers now routinely compromise various automated build pipelines and developer IDs. Another VS Code extension, marketplace, security leak, and even Microsoft owned repositories have been recently affected by developer environment attack, and arguably even the GitHub source was stolen and sold on dark web for $50,000 to $95,000. Yeah. So unless the platform owners like Microsoft VS Code extension or any other Cloud Code or Codex plugin ecosystem or agent skill repositories, until they all implement the strong security guardrails, we have to deal with this by ourselves. And here is another paper about the recent incident on the Microsoft side, and here the authors have a good point. The developer environment is now an attack surface. So I'm a software developer and my computer has accidentally became an attack surface in 2026. So I really want to deal with that and not to be a target for a cyber security attack. Those were the Visual Studio Code extensions, but supply chain attacks are not limited to Visual Studio Code. It would have been really easy to solve. But unfortunately, supply chain attacks in 2026 became really huge. I mean, if you look only at the April to May, there are, I don't know, how many, 12 high-stake attacks. And many of those attacks target very popular open source maintainers. Like on multiple occasions, attackers used social engineering to steal tokens from computers of prominent open source developers. And then they used those tokens to distribute worms through the open source packages and steal even more keys. We don't know how many access keys were stolen, so we are in the middle of a cybersecurity snowball, and the fight is ongoing. Another seemingly unsolvable security risk is called prompt injection. And here I would like to try a demo. I've prepared a Docker container, a very bad Docker container, and the prompt injection prompt. I will copy it and I will go back to my Visual Studio Code. This is an empty directory on my computer, and I will ask the agent, please help me to bootstrap POC, proof of concept. Bang. What will the agent do? By the way, I'm using the automatic model selection on a free GitHub Copilot account. I just use my GitHub login to get free access to this model. And it's trying to download the gist. Let's see. I've actually tried it before. Now it checks whether I have Docker or Podman on this computer. Some more reasoning efforts. So this is the Bazel workspace, yes. And now it runs the podman command with the current directory mounted inside. This is the correct behavior. So in this case, the agent understood that this instruction is a prompt injection. So here I'm instructing the agent to mount the entire root directory inside the container. Unfortunately, the large language models are stochastic random number generators, and my previous try in the morning, it actually decided to call this command. So we can try again, and maybe it will actually run. But basically what happens is that the large language models are trained to be instruction followers. They try to help me to finish the task, even if the instruction may be hostile. So if the agent needs to solve a bug, and for instance there is a bug with some open source product, then it may go to a GitHub page and maybe find instructions which seemingly can solve the problem, but an attacker may leave some malicious instructions to execute some bad command, which can actually own my computer and steal the data. This is what I'm trying to show, but apparently the auto-selected model is very smart. At least it worked in the morning, but it doesn't work anymore. We'll see how it goes. But in the meantime, I would like to go further and look at the next topic of our program called CDEs. Look, it decided to destroy my computer on the third try. So I tried 2 times, it didn't, and the third time it decided, okay, now I can give the entire root directory to this unknown Docker container. And if I click allow, then something happens, something inside this container. I'm not going to do it because this is my container. It will create some file in the home directory. But you see the point. The large language models cannot be trusted with security, at least not as of now. There are maybe some well-trained large language models which are able to detect that kind of subtle prompt injections, but yeah, let's actually look which model was that. It was my code 1 flash. What is that? Microsoft AI code 1 flash, maybe? I don't know. Yeah, let's go. So how to protect against both of them, or at least minimize risk? Yeah, the first the first row of defense is cloud development environment. This is the step in the right direction when the agent is running in a separate, isolated execution environment, such as a Docker container or a virtual machine, so that the secrets on my computer are protected and the agent cannot access my hard drive directly because it is given only a copy of all necessary data. For example, Visual Studio Code has a few mechanisms for that cloud development environment or development environment in general. Here is the example of a local container. So the source code directory or the workspace directory is mounted as a volume inside the container, and there is a Visual Studio Code server. It's a headless process which runs inside a container, so that the user interface can send all the operations through a channel to through a socket to this VS Code server. Another example is remote development using SSH, where I can start a virtual machine and connect from Visual Studio Code through SSH tunnel, through SSH connection to that remote virtual machine, and again VS Code will automatically download the VS Code server on that machine and start it. In this case, I have to copy the source code manually because there is no standard way to mount local directories on the remote machine, although there is also SSHFS, for instance. There are many ways in Linux, but if the client-side Visual Studio Code is not running on Linux, then it is easier to just copy the code to the remote machine. Yeah, this is Visual Studio Code, but in general, these cloud development environments are available not only in VS Code, but also in JetBrains IDEs, and there are various services, so subscription services which implement this. So there is a service called GitHub Codespaces. It's an extension apparently. I never tried that. There are others like Coder, Gitpod. There are also open source variants. So coder.com, they also publish their source codes on GitHub under AGPL, so quite nice. Didn't try myself, but apparently they support various cloud providers and Kubernetes through Terraform. There is also Kubernetes special interest group called Agent Sandbox, and it's a Kubernetes operator which can spin up the sandbox environments dynamically based on custom resource definition. It's like a Lego for agentic sandboxes. What else do I have? Oh yeah, and another notable example of remote Visual Studio Code is Code Server. It's an open source version of github.dev. So VS Code has the possibility to run Visual Studio Code in a browser window. So here I can just replace github.com with github.dev, and this repository will be opened in a Visual Studio Code inside the browser. But obviously I can also run Code Server, and I try that. It takes only maybe 5 minutes to set up. It's just one package to be installed and one HTTPS port to be forwarded, and that's it. I got Visual Studio Code running in my browser with everything remote. So on my computer there was only the browser and I didn't have to install anything. I should probably incorporate this type of workloads, this type of sandboxing as well. Okay, so I need to go back to my presentation. We discussed the sandboxes, but sandboxes are not solving the issue of credentials that need to be used inside this cloud development environment. So if an agent needs to access some network resources such as Git repository, or maybe needs to search the corporate database, then the agent needs to connect to those resources, or it needs to connect to the MCP server, and the MCP server needs to connect to the company resources. So the question is, which credentials shall be configured inside this isolated sandbox? Probably those credentials shouldn't be my personal credentials, because my company credentials are quite wide. I can see a lot of data. I can access a lot of various systems. And some small development environment where I work only with maybe one Git repository and maybe one backlog. It's too much to give this agent an access to the entire company ecosystem. That's why the industry created the Zero Trust architecture. Let's look at the document. Yep. This is the document. National Institute of Standards published 6 years ago. The standard called Zero Trust Architecture. And this particular standard is a guidance which describes the security model for enterprises, how to implement the continuous verification for each and every access attempt, and go away from the implicit trust like the firewall-based access controls. This security framework gained widespread adoption in large enterprises and in regulated industries such as healthcare and financial services. But the implementation complexity is so high that only the wealthiest companies can afford to build the entire internal IT landscape to fulfill these requirements. And it's not only authentication authorization, it's also transparency, logging, monitoring, detection, prevention. It's a lot. So instead, many implementers would try to secure a small critical IT perimeter. For example, a payment processing team will be given a separate office somewhere on the other side of the town, and they will have the strict security control on the door. Then they will have the non-transparent windows. Then they have all those authentication, authorization, dynamic credentials, and so forth. It's quite complicated. Therefore, it's easier to start small. But if it's complicated, it doesn't mean we shouldn't do that. That's why Anthropic released a white paper called Zero Trust for AI Agents. It's quite fresh and it's quite good. If you scroll down, there is a link to this PDF file. Yeah, Zero Trust for AI Agents. It consists of 5 main parts, at least relevant for me. The first 2 sections are for cybersecurity managers who want to understand agentic threats and compliance landscape, whereas the next 3 sections are mostly interesting for engineers who need to plan and implement those zero trust controls inside their company IT infrastructure. Let's look at the implementation part. So how to apply the zero trust to agents. Here Anthropic shows 3 levels of implementation, so 3 levels of complexity: foundation, enterprise, and advanced, or advanced. So the implementers can start small with the foundation level and slowly upscale the protection. So for instance, go from role-based access control to ABAC. I don't see Zanzibar here. Maybe it's continuous authorization with yeah, probably this is Google Zanzibar or OpenFGA. Yeah, and each and every aspect of the agentic cybersecurity is described really well, at least from the standpoint of zero trust for AI agents. So it could be a good list of checkboxes you want to tick during the initial design. Unfortunately, some of the proposed security measures are slightly naive or unrealistic. For example, there is a section called service authentication. Yeah, I was looking for it. And here they write that agent identity solves half the problem, but agent must also prove that identity when accessing databases, APIs, and other services. Wow. Does it mean that the agent needs to access databases and APIs directly? That would be quite complicated to do in the existing environment. So if my agent takes a token and uses this token to access the company resources, and the company resources are sending the telemetry to the central logging system, that can work, but this means 2 things. First, the agent needs to have a separate set of credentials which are given or issued from the central server. And the second, the company resource needs to be able to limit the access to the specific operations required by this agent and nothing else. And of course, because the agent has its own, so the agent instance has its own credentials, we can also track all the operations through all the backend systems inside the central open telemetry server or whatever the telemetry server it is. On the first look, it's okay, but if you think further, for example, if this company resource is an Azure DevOps server. If I need to allow each and every agent to access this Azure DevOps server, I cannot simply issue a personal access token, because personal access token cannot be limited to one repository, to one project. My personal access token will give access to the entire Git and backlog of the entire company, right? So I would need to create a login for the agent and buy the license. So the agent will need a human license. It's an overkill. It's expensive. But what is the alternative? The alternative is to use personal access tokens and limit the agent to the very precise token. So my company has to migrate from Azure DevOps to, for example, GitHub Enterprise, because GitHub Enterprise will allow each software developer to create personal access tokens for their personal AI assistants, AI coding agents. So they will be able to create very precise personal access tokens, but this also means that the entire company needs to migrate. So either way, both variants are expensive and complex. And even if the company solves this problem, buys the licenses or migrates to GitHub, it doesn't solve the problem of the token theft, because the personal access token is just a long string of symbols. If it's stolen by an attacker and it's a GitHub, then attacker can access the repositories directly from their computer somewhere on the internet, because most of those systems are realistically nowadays cloud-based, software as a service. So yeah, this classic zero trust is really complex. That's why Anthropic writes in their document that the agent identity must be cryptographic, and ideally it has to be stored in TPM or HSM. This is, how to say it, inside the cloud, HSM is probably the most expensive service that you can ever get. And TPMs, okay, they're in every laptop in the world, but in order to give an agent access to a trusted platform module, you will have some problem explaining to the agent how to use it, because TPMs are very dumb devices with CLI or C++, no, actually C API. It's really hard. So it is really an advanced level. But otherwise, if it's not implemented and the token is a pure plain text environment variable or a file on disk, then it can be stolen. That's why Anthropic writes that this should be X509 key pair. Okay, now I understand the problem of the classic zero trust. What I wanted to say, oh yeah, I wanted to say how to solve this problem. I would like to suggest Anthropic to actually extend this table with a fourth tier above the entry level, above the foundation, and call it, I don't know, identity proxy tier, pre-foundation. Why? Because, I skipped this. Because in the Zero Trust Identity Proxy, it is possible to implement the very same controls, but don't replace the central IT systems, the existing systems. So what I want to do in the Zero Trust Identity Proxy is I want to augment, I want to limit the existing security controls with an extra layer of protection, verification, and authorization by implementing this Zero Trust only for the agents and implement it as an authorizing proxy or identity proxy. If you think about access rights needed for each of my agents, you may notice that none of my agents actually need more permissions than I do when I log in with my browser into my corporate account. In 99% of the cases, the agent permissions can be created by simply limiting my personal account permissions with a set of rules which will limit which operations my master key or user identity can perform on some central company IT system. So if I could give the agent their own keys, but when the request leaves the proxy perimeter, I will validate it and replace it with my real key, then I don't need to reinvent the entire IT ecosystems, and I can still control all the agents. It was not very easy before AI agents became a thing, but with the invention of MCP servers, it became very possible and realistic and easy to do. I will show it later today, and now I would like to show the actual implementations of such Zero Trust Identity proxies, because obviously I didn't invent it. It was already implemented before. And it didn't start with MCP, but it is very relevant. So here is Arcade. It's a recent presentation on some conference, MCP Dev Summit, because Arcade is an MCP proxy. So their gateway allows to manage agent identities and assign access for each identity to specific MCP tools on the specific MCP servers, so that the agent can see this Arcade MCP gateway as a single MCP server, which exposes the number of tools, but only the tools which the agent needs. So an agent connected to this MCP gateway, it can only see the tools it needs, and it cannot see the authentication, because the token, the access token of the agent, is different from the access token which the MCP gateway will be using to connect to the outside world. Namely, it will be my normal user identity, such as auth to some client credentials flow, whatever it is, configured in the MCP server itself. But the agent will not see this actual internet token. It will have its own authentication. The same idea is implemented in an older project, which is called Teleport. Teleport is also an identity proxy, and it can authorize MCP servers, but it can do much more than that. It can authorize and proxy SSH connections, Kubernetes servers connections. It can proxy various public cloud consoles. And although apparently Teleport was developed as a human-centric authorization and zero trust proxy, it is still very useful for securing AI agents and software development sandboxes alike. Yeah, so it could have been a very good candidate for my personal development environment. Uh, unfortunately, it has a strict license, so I cannot apply it to bigger companies. I can use it for myself, but not for my company. Another notable example is Git Proxy. This is an open source MIT license GitHub project, very good. What it can do, it can give each agent inside separate cloud execution environments its own token. And Git Proxy can be configured to allow each and every token only access to a specific repository. And not only that, it can allow a read-only or read-write access to each and every repository connected here. And obviously the tokens on the agentic side, on the back of this proxy, are not the same tokens as the Git proxy is using to connect to the actual GitHub or Azure DevOps. This is already a long way forward to the actual security of a sandbox, because even if this token is stolen, it will be useless for an attacker, because an attacker needs to use this token from inside the isolated environment, and it's really hard. So it's much harder than stealing a token or exfiltrating it through email or whatever it is, through the prompt injection, and then use it directly to connect to GitHub. If the token is invalid on the internet, it already solves a lot of problems. And in fact, I use this open source project inside my platform, so you will see how it works later. I found some other projects like hoop.dev. Apparently, it's highly focused on securing various databases, SQL databases, but they also claim to have support for various other protocols. I didn't try it myself, so I need to invest more time into studying this particular project. Yeah, so now we saw the cloud development environments. We saw the zero trust proxies, and the obvious question is why not to combine them both together? And this is actually what I did. I wrote a runabout. Yeah, this is the diagram of internal security. So here on the left is the cloud development environment, an isolated sandbox. In the middle, there is a zero trust proxy, which validates all the requests coming from inside the isolated sandbox. Each proxy has settings, like authorization settings, so the user can provision the proxy, can configure the access rules for each and every container. And by the way, this whole thing is running inside Kubernetes, so it's very similar to this project, to Agent Sandbox, Kubernetes Agent Sandbox. It's also a Kubernetes operator, but it's much more integrated. It's like all-in-one solution, very user-friendly. It's a self-service application which incorporates the sandbox and the zero trust proxy as a single package. So in principle, on the left, there are fake tokens, like fake Git credentials, fake MCP credentials. And on the right, there are actual real credentials which are never accessible to the isolated workload, and those credentials are configured by the user dynamically. So it can be the user's personal access, like single sign-on on a company portal, auth, client credentials flow, device registration flow, whatever it is, so that the proxy can still act on behalf of the user, and the central IT don't have to provide a separate identity for each and every isolated workload. But here you can see this arrow to OpenTelemetry server. Every proxy has its own telemetry sync so that the user can see all the actions which the agent was performing on the proxy, and the user can set up alerts, for instance, analyze, do the postmortem if the agent was hacked, and even in the future, who knows, maybe we can program together a system which will automatically look at the logs and will switch off the misbehaving agent as a preventive measure, so that the user can come later and see what happened actually inside this container. Because you see, all the large language model requests and responses are also connecting to the external large language model backend APIs through the proxy, which means that the OpenTelemetry server does have all the inference requests and responses. So everything is saved. Previously, such a total control proxy wasn't really practical, because we tend to use browser-based interfaces and various graphical user interfaces. And the browser traffic is really hard to inspect. Browsers are designed to actively resist the inspection of HTTPS protocols. If a company wants to inspect HTTPS traffic, then it will be called man-in-the-middle attack from the standpoint of a browser. So companies needed to use secure web gateways such as Zscaler or Netscope, I guess it's called. Those systems can decrypt and inspect the TLS traffic, but they cannot encrypt it back with the same key after inspection. So they had to use fake certificates in order to re-encrypt the TLS session, and therefore each and every client, like a browser, needs to be configured with a custom certificate authority. And if you consider how many browsers there are, and each browser has its own way of configuring the certificate store, and there are also graphical user interfaces for various other programs which also use HTTPS protocol. And each programming language will have its own certificate store. Like a famous example is that Java doesn't use system store. It uses its own certificate store by default. And Python sometimes wants to use its own certificate stores. It's a nightmare. So in order to inspect the browser connections, it would be a lot of work, but we are very lucky because AI agents don't really like to use the direct internet connections. AI agents like to use MCP servers and other tools which are provided by the agentic harness. Therefore, we have a really good chance to create such a proxy wall, such authorizing zero trust proxy without decrypting TLS traffic, by simply inspecting the payloads inside the MCP server and maybe inside the Git requests. I will show how the Git works today, and the MCP proxy will be shown in the next video. But I want you to understand that this is our chance to make it right. So I took the chance and made it. At least I started to make it, and I hope some of you may join my efforts to create such a total control environment for AI agents. So it's demo time, and I want to show you how it works. So this is the interface. By the way, this is the main page, and this is the web interface. I've logged in with some test account. So I would like to continue showing how to use this runabout platform with VS Code. In order to do that, I need to provision an empty container, Ubuntu container inside Kubernetes. Click. So 2 clicks, I get an empty container for the new project. Basically, it became my best practice. If I need to work on a new project, I do 2 mouse clicks and my local virtual machine with runabout on my computer is spinning up the new container. How much does it take? Maybe 30 seconds, I don't know, we'll see. In the meantime, I will try to provision SSH access. Let's open the second tab here and launch the app. Okay, it's up. Yep, there are some processes inside, basically nothing. This is a Kubernetes container running in user namespaces, rootless mode. So I am root inside containers, so I can do apt update. And it will work because I'm kind of root, but actually this is not real root, it's just a user namespace. So inside Linux machine, this container is unprivileged, some random number. So I want to get SSH access. This is the web terminal, but I want SSH access, so I'll provision an add-on called SSH jump host. Yep, and it is ready. Now I need to configure it. I need a public key, so let's go back to the Visual Studio Code. So here's my Visual Studio Code, and I can SSH key gen. I will override the existing file because it was from my previous attempt. Okay, so the key was generated. This is the public key. I will copy it into the add-on settings here. Create a new public key. This is the new key. Bang. Settings are successfully saved. Good. Now I want to assign this SSH add-on to my bot. Here in the bot settings, I can click assign and save. And what happens now in the background, Kubernetes operator will go and configure an SSH server. Look, there was no SSHD. Now there is an SSH server running inside this container, and also there is a new folder .sh. There is no authorized keys yet. Now it is. So inside this authorized keys, the Kubernetes operator wrote my public key. Oh, where is it? Strange. I thought I configured it. This is really strange. Okay, let's try it again. Okay, it is configured. Somehow this web UI doesn't understand it. Okay, maybe it has something to do with 2 tabs simultaneously. Yeah, let's close it and see how it goes in this central. Yeah, it is there. Okay, so the Flutter web UI is not particularly happy when I'm doing it in multiple tabs. Okay, now the SSH add-on is configured and it is assigned to this bot. Let's rename this bot. Let's call it demo1. Save. Now I can SSH into this bot. I will copy the command. We'll go back to terminal on my computer and just SSH. Ooh, obviously I tried it before, so I need to delete the key. I use the same container name. All right, so I'm inside. I'm inside this container, and if I do sleep 1, 2, 3 and go back to the terminal, to the web terminal, here it is, sleep 1, 2, 3. So this is the same container, but I access it not through the web terminal. I can access it through SSH now. Let's configure the SSH config. So here is the example of an SSH config. Here I can copy the entire thing and put it into SSH config. So here doc works like this. I write it into my .ssh config at the end. Insert and write EOF and a file. Bang. Now this is written at the end of the file, but I want to replace the entire file because I generated dynamically and there are a lot of rules inside this file. So I will completely overwrite it, and the next time I can recreate this config from my .files repository. Right, so now, oops, I did it inside the container. That was wrong. I need to do it on my computer actually. Okay, cool. So I have overwritten my local SSH config completely, but you shouldn't do that. You should use like double brackets so that it is written at the end of the file. Anyway, now I can try to SSH to demo1 and it works. Cool. If I can do that in terminal, then Visual Studio Code can do that as well. Look, here in the bottom left there is a connect to host, and it's a connect to SSH host. So I can write demo1 here and connect. Now what Visual Studio Code is doing, it's trying to SSH into the remote container, and it tries to install the Visual Studio Code. Now it installed the Visual Studio Code inside a container as a VS Code server, and this VS Code server is trying to download stuff from the Microsoft website. How shall I know? I go back to the settings page of the bot, and look here below I can see all the network connections which this particular container is trying to establish. It tries to connect to update.code.visualstudio.com. Alright, I can whitelist it with VS Code install description. Bang. Now VS Code can connect to this, but it tries to also connect to some other update.visualstudio.com. Okay, now it's downloading. Apparently it wasn't enough, and it needs some other. Oh, VS Code download PRSS Microsoft.com. Oh man. Alright, I'm tired. I will open the firewall for 1 hour and see what happens. Now it's downloading, obviously, because this whatever PRSS CDN wasn't available. I didn't want to spend time allowing it manually, so I opened the firewall. Now the VS Code inside the container was able to use internet access in order to download the VS Code server, and now it's running. Perfect. Now I have two windows. One window is on my local computer. This is my local VS Code. And here in the bottom, you can see it says SSH demo 1. What does it mean? It uses the SSH connection, which is called demo 1 inside the SSH config. So if I click open folder or whatever it is, the terminal, it's actually on the remote computer. So here I can say mkdir src to create a folder for source files. Now I can select it, and it's a folder inside the container. So whatever my agent does in this window, it will not affect my computer, and it is already quite good protection. But of course, it's not the best, because we just use the cloud execution environment without any proxy. So if I want to download some Git repository inside this container and start working, I will have to use my actual public internet-facing Git credentials. This is suboptimal, and instead I would like to show you another DON. So namely, Runabout has a few zero trust proxies. There is a Git Proxy. I'm gonna install it now. And it's installed. It doesn't really need anything. There is also large language model subscription proxy for GitHub Copilot subscription, or Codex subscription, or Cloud Code subscription. This will send telemetry to OpenObserve. This is the OpenTelemetry server, which you can also install in one click. Bang. What else do we have? We have a Postgres database, so you can install a Postgres database in one click, and there is an OLA LLM proxy. This can be used for load balancing and telemetry of the large language model API access. Like for instance, if you have OpenRouter account, you can connect it to OLA as a backend, but also send telemetry to OpenObserve, and so forth. Yeah, OpenObserve needs to be upgraded. Right, so our today topic is limited to SSH add-on. To Git add-on. Inside the Git add-on, I can create as many Git servers as I want, and each and every Git server will have its own prefix on the internal Git server. So inside the isolated environment, a Git command will need to connect to a Git proxy address. So the Git proxy address will have the valid valid HTTPS certificate, but it will understand which Git server to connect to by using this prefix. Let's say I want to start developing this open source project. It's called OLA, the LLM proxy, and I want to give access to this repository inside the Runabout container. But imagine this project is not hosted on GitHub with personal access tokens. Actually, it was the previous example. Oops. Let me quickly re-authenticate myself with two-factor authentication. All right, and we are back. So I will generate a fine-grained access token on GitHub, but I will not limit this token, because here I can actually define not all repositories. I can select one particular repository for this token, but I don't want to do that, to show you that it is also possible to limit the access on the runnable side. So here I will allow the access token to actually read and write, so git pull and git push. Yes, and this is the token. I copy it and I continue setting up the Git Proxy add-on. So the prefix will be GitHub 1, or what was that, demo 1. Description is personal access token on GitHub. Wide open personal access token on GitHub. Very bad practice. GitHub.com is the HTTPS server name, my username, and the token. Okay. Now, when the credentials are created, let's create also the access policy. Let's call it demo, let's call it all read write, and assign the bot. Cool. Now we can actually define what this policy gives for this particular GitHub token. If I want to allow access to this repository, I can define it, or maybe I would add also the .git as an extension, because sometimes I can clone with the name, and sometimes with the name .git. I just simply allow both. And for this repo access profile, we will allow read-write, but we also create the second policy, which will allow any other repository to read. So my agent will be able to clone any GitHub repository, but it can be able to git push only to this other repository. Good. Now we saved it, and we go back to the bot. We assign the Git Proxy add-on to this bot. And what happens now? Oops. What happens now? The Visual Studio Code complains. Why? Because Kubernetes has stopped the container, and container is now restarting. It takes maybe, I don't know, 30 seconds. We'll try to reload, and the VS Code will try to re-establish the SSH connection. Because I reconfigured the add-ons, and this add-on requires creation of configuration files inside the container, Kubernetes operator restarted the container. This script is actually configuring Git for a transparent Git operation. If we look into .git config, we'll see a magic happening. So this is the token for authorization of this agent environment on the Git proxy. The Git proxy is here. It's an internal address. And everything which starts with github.com will be rewritten to Git proxy run a bot /demo1. Do you remember this is the prefix? So if I want to clone the Git repository that I allowed access to previously, this repository, I just copy the name and say CDEs empty git clone this name. It works. But if I would try to curl this address, oh, it works. Okay, sorry, I forgot to switch off the firewall. Let's remove the folder, go back to the interface, and actually disable the firewall opening. Now I cannot access to GitHub.com, but I can still do a git clone. Can I do a git push? Let's see here. Remember, I gave the proxy, the Git proxy, a token with full access, and this Ola read-write has read-write access to this repository, so git push shall work, and yes it is. But if I go back into the settings, and here instead of read-write I say that this group of agents can only clone or git pull, then the git push shall fail. Oh, yeah. Git push still works because I pressed save here. I didn't press save here. Now it doesn't work. Okay, everything is good. Works as designed. But if I allow pushing to this repository, then bang, it works again. Okay, cool. It wasn't the system, it was me. Let me check what's on my plan. Yeah, I showed you the identity proxy together with the sandbox. To wrap up, I want to show the firewall features. So inside this demo one, you already saw that this magic firewall, it can actually see the host names, and it can allow each and every host name by clicking whitelist now button. But it can be a lot of work. So instead, when I create a new development environment, I usually switch on this network auto discovery mode. So let's say I want the agent to be able to connect to Wikipedia. So curl wikipedia.org. Oops. And it doesn't work. It cannot connect. It times out. But when I switch on the auto discovery learning mode and save, then curl to Wikipedia works immediately. And when I come back here into the settings page, you see that the Runabot backend automatically recognized that this container is trying to connect to Wikipedia, and it created a record with learned at. Cool. It showed that the first connection was denied, but the rest of the connections worked flawlessly. Oh, it also added the Microsoft telemetry, so Microsoft knows that I started Visual Studio Code as root. Now, when the learning process is finished and I made all the usual actions to establish the baseline, I can now switch off the learning mode and go through the list one by one. So for instance, I don't want to allow telemetry, I can delete it and save it again. And I didn't have to click the allow button manually. Right here, I just enabled the learning mode. So when your network administrator will see that They don't need to set up fake certificate authorities and configure browsers and all this Z-scaler nonsense. They will be really happy when they see this magic firewall. Okay, so on my plan there is only one thing left, and I want to say a few words about why I do this and how you can start using Runabot inside your company. My initial thought was to open source the Runabot platform in order to gain trust from end users. But unfortunately, the recent advancements in AI-assisted vulnerability search and the corresponding wave of AI-generated exploits made me believe that it's counterproductive to open source the entire system, because it's a cybersecurity defense software, and I don't want to help attackers to actually use large language models to find zero-day vulnerabilities. That's what happens with Linux kernel and all other prominent open source projects right now. When some security bug is fixed and the fix is pushed, even if the CVE is not published yet, there are many attackers who are actively looking at the diffs and sending them automatically into large language models in order to produce the working exploits. Therefore, what I decided to do, at least to try to do, is I would like to organize a community of Runabot users. You may call it a club, or in Germany we call it Verein. We have a culture of such clubs where we work together to achieve a bigger goal. So I want to work together with bigger companies who have their own staff developers. If those companies want to validate the source code for security and to make changes to the source code, then I will be happy to provide this source code for free to those tier 1 club members, to bigger companies with their own software developers. But I would like to ask in return for those tier 1 club members to publish the results of the security audit on their website, so that I can reference the websites of big companies, prominent figures in the IT industry, and say to my tier 2 Runabot customers, look, those big companies employed all their AI resources to validate the security of the source code, which is running, so you can trust those tier 1 companies because we develop this platform together. And the tier 2 Runabot customers will be able to profit from the results of our work inside the club, but they will not have access to the source code from the very beginning. If the customer in the tier 2 level would say, I don't want to buy the Runabot platform as a service, I want to deploy it on my computers, on my servers, and I have a member of staff who wants to make a security audit and develop the source code, this is totally fine. Anytime, convert from tier 2 to tier 1, become a club member, get access to the source code, to Git repositories, to the chat, to the conferences, and whatever it is, the activities inside the club. But it will be the inner source from the very beginning, at least for now, because of this because of this wave of AI-assisted exploits. You can read about this particular model on the website, runabot.de or runner.bot, run-a-bot. If you have any questions or ideas, feel free to comment. I will try to answer. If you want to ask some other questions, then there is an email on the homepage at the very bottom. Contact us, info@runabot.de. I will also try to post updates in a pinned comment under this video. And I'm gonna start the limited invite access for software developers. So if you're a software developer and you want to try this platform for yourself, I may give you access to my production server. As of now, the registrations are opened. You can register, but your account will not be activated. But it may change in the future, depending on the feedback from my colleagues. Basically, there are only 2 people in the world who know about existence of the system. You will be the next. Thanks for watching, and see you soon. Bye.